Right. Okay. Mm. Okay. So I think I have been told that I have to change the color. Why is it showing? Yeah, I've been told that you already know some measure theory, and the purpose of my lectures today and over the next few days is to learn the so-called LP spaces. Okay. Yeah, just give me a second.
Sir, is it possible to increase the width?
Possible to increase what?
Width of the files, sir.
Okay.
Length is, if possible. Yeah.
How about this?
Yes, sir. Very good. Yeah, this is fine.
All right. So we shall learn LP spaces. Okay. LP spaces LP space is a vector space. We'll come to it. Today, I'm not going to introduce LP spaces. Instead, I'll start with something elementary, namely convex functions. Okay. You can stop me at any time, ask questions, and whatever. I guess some of you have seen, at least some of you have seen convex functions before. So what are convex functions? So definition says, so let AB be an interval, the whole real, that's why A could be minus infinity and B could be plus infinity. Oops. Real valued function phi defined on AB. So phi is from AB to R. It's called convex, is called a convex function if phi of 1 minus lambda x plus lambda y less than equal to 1 minus lambda phi x plus lambda phi y for all a less than x less than b, a less than y less than b, and 0 less than lambda less than 1. So lambda is between 0 and 1. This thing 1 minus lambda x plus lambda y, or lambda x plus 1 minus lambda y, which is really the same thing. I mean, the role of lambda changes. They are called the convex combinations. So 1 minus lambda x plus lambda y is called a convex combination of the points x and y. Convex combination, not linear combination. Convex combination when it's of this form. And the demand is that the phi value, that means x and y are 2 points, and 1 minus lambda x plus lambda y is a point in between. If you think of x and y as 2 points on the real line, 1 minus lambda x plus lambda y is just a point in between, and any point in between is in fact of this form. Okay. The value of phi at a point in between is less than equal to the convex combination of the value of the points phi x and phi y. So when you take 1 minus lambda phi x plus lambda phi y, you get a straight line joining the points x phi x and y phi y. So what I'm saying is, because there's nothing better than actually drawing, so the function is something like this. So suppose this is x, and perhaps that is y, and this is the line. This is the line. I need to erase this. Okay. That's the line, 1 minus lambda x plus lambda, 1 minus lambda phi x plus lambda phi y. So that what's being said is, at a point in between, say here, the value is less, the value of the function. So this is phi. The value of the function is actually less than below, the value of the function is below the straight line joining the points x phi x and y phi y. Is that clear?
Yes, sir.
Good. Examples? Well, I mean, the way I have drawn it, obviously, the first example you can think of is e to the power x. E to the power x exactly looks like this. E to the power x is, in fact, a convex function. You can either directly prove it, or I shall soon prove a lemma, and you can prove from there that e to the power x is a convex function. You don't have to worry about it right now. I'll give many examples of convex functions. Thing is, doesn't really have to be that smooth. Okay, it could have corners, like something like this. Has corners, so not always differentiable. Continuous, but not always differentiable. And nevertheless, as you can see, this is a convex function. Or a plain and simple mod x graph is also a convex function, trivially. Okay. So could have corners, need not be differentiable. So these are examples of convex functions. Now, I think the first thing, I'll call it an observation. Phi is convex if and only if maybe I should have motivated this a little bit. Look at this ratio on the screen now. So phi is convex if and only if you have points A, S, T, U, B, and phi t minus phi s by t minus s is less than or equal to phi u minus phi t by u minus t. So what are these ratios? So your points are maybe like this, right? STU. Now, when you do phi t minus, okay, where, fine. When you do phi t minus phi s divided by t minus s, so phi t phi s by t minus s, so you notice this is your phi t minus phi s, and then you are dividing it by t minus. Phi t minus phi s divided by t minus s is the vertical line divided by the horizontal line, is the tan of the angle. All right. So when you do it for the pair ut, you will get tan of another angle. And you can see if I'm from the slope of the curve that the tan of the angle is actually increasing. That's Well, you might suspect that it's because the curve is increasing. Okay, take a decreasing curve. So suppose this is your S, this is T, and that's U. Here it will be, so phi t minus phi s here is actually negative. Phi t is less than phi s. Whereas here, of course, trivially it's kind of positive or at least zero. So you can see again the thing is increasing. So this is being satisfied. Am I clear? If not clear, let me know. I'm trying to motivate how one gets this idea. Phi is convex if and only if something I've written, and I'll prove it. How does one get such ideas? One gets such ideas by looking at the graphs of convex functions and guess from there that maybe this is true, and then only then tries to prove it. And how do you get this? Well, this is, as I showed you, it's the phi t minus phi s is the vertical distance. That is, you are subtracting phi s from phi t. So it's the difference between phi t and phi s. That's a vertical line. T minus s is a horizontal line. So it's obviously tan of some angle. You're dividing a vertical line by a vertical length by a horizontal length. It's a tan of some angle. So tan theta is increasing. That should be clear to you. That is the motivation for this. So convex functions have a certain kind of graph. That's what is being said. We'll do better than this. We shall find better criteria. Okay. The proof is as follows. Let me number certain equations. I'll call this 1 and I'll call this 2. So you see, t minus s by u minus s plus u minus t by u minus s is 1. And so I can take one of them to be lambda and the other to be 1 minus lambda. Okay, so we get phi of t minus s by u minus s times u okay. That's just from definition of convex function. If phi is convex, then this holds. All right. What is the left hand side? It's so u minus s is a common denominator, and on top you have t minus s into u, which is ut minus us plus su minus st. So us minus us plus us cancels, and you get tu minus ts, which is t times u minus s. That u minus s cancels with the denominator, and you are finally only left with phi t. Okay. So on the left-hand side, I have only phi t, that's less than equal to something or other. Now I do a little bit of a simplification. What I need is this. I need 2. So I have gotten phi t less than equal to something or other. So I do phi t minus phi s. Less than equal to t minus s by u minus s phi u plus this thing, u minus t, u minus 1 minus 1 phi s, and I'll get u minus t minus u plus s. So that will actually give me s minus t. So that's equal to now the fraction is common. Right? Okay. So if phi is convex, then this is true. This is exactly the equation 2. Conversely, if equation 2 is correct, so conversely, two holds, then, so two holds meaning this thing holds, which is at the top of the screen now, that holds, that is 2. I want to show that phi is convex. That means I have to follow the definition. That means I have to show phi 1 minus lambda x plus lambda y less than equal to 1 minus lambda phi x plus lambda phi y. Then so I shall take t to be 1 minus lambda x plus lambda y, s to be x. Remember the order, s less than t less than u. So I'll take x less than 1 minus lambda x plus lambda y less than y. X and y are the two endpoints, and the convex combination is something in the middle. T minus s will be lambda times y minus x, because t is 1 minus lambda x plus lambda y. Less than equal to phi y minus y minus x cancels from both sides, and I'm left with, let us see what I'm left with. I'm left with 1 minus lambda phi no, minus. So finally, after some cancellations, that proves phi is convex. So now we have proved an equivalent criterion for convexity. What we have done so far, let me quickly recall, defined what is a convex function. That's in equation 1. This means, graphically, it means just the graph below the definition, that the graph should be like this. The graph cannot be like this. It cannot be the other way around. So it cannot be like log x, for example. Then the graph is above the line. And that's exactly the opposite of convex. Then minus of that, in fact, will be convex. Example is e to the power x. E to the power x has just the graph like that. But of course, I said that I shall formally prove that e to the power x is convex in a minute or two. Next, need not be differentiable, need not be that smooth. So curves with kinks. And then we have just proved that the convexity property is equivalent to a certain ratio being less than equal to certain other ratio. Okay. All right. This is what we just proved.
Oh, excuse me, sir.
Yeah.
So what you proved and what you stated are a bit different.
Let us see.
Yeah, here the result is phi t minus phi s, and yeah, this right hand side there is u minus phi s divided by u minus s.
Right. That
Yeah, here
that's the
when we
problem.
are
Just a
able
minute.
to prove.
That's right. That's right. You are correct. Just give me a second. Thank you. And you are correct. So phi t less than equal to this. Phi t minus you were right. This has to be corrected. Just give me a second. Give me a second. It has to be phi u minus phi t by u minus t for, I mean, for us to be able to use it later. So let me see how we can actually do that. Just give me a second. Okay. So we have gotten this far. We have gotten to the state that phi t minus phi s less than equal to t minus s by u minus s phi u minus t minus s by u minus s phi s. Fine. I want phi u minus phi t on the right hand side. The best thing might be, okay. So I write this phi t as, maybe not. I subtract and add a t minus s by u minus s times phi t. Now, I bring the last term to the left-hand side. So I'll get phi t minus phi s times 1 minus t minus s by u minus s less than equal to, I still have a problem perhaps, but we'll see. And what is 1 minus s, 1 minus, so that is u minus t, or phi t minus phi s u minus t by u minus s. Right. So it was a bit of an algebra which I missed. So note that we reached the top line of the screen, and from there I went into a different direction. Okay. So what I now do is, since I want phi u minus phi t, I do that. I just put in that phi u minus phi t, but phi u comes with a coefficient. So I have to put in the phi t with the same coefficient. I subtract that and add that. All right. Perfect. So I'm left with now phi t minus phi s is there on both sides. So I bring one of them from the right to left. So I'll get 1 minus phi t minus phi s times 1 minus t minus s by u minus s. That's less than equal to t minus s by u minus s, phi u minus phi t. 1 minus t minus s by u minus s turns out to be u minus t by u minus s. So u minus s is in the denominator of both sides. That cancels, and then I have. Is that all right now, Anjali?
Yes, sir. Yes, sir.
Okay. And the converse direction we have proved already. All right. Okay. Now, I mean, when you look at this, which is at the top of the screen now, when you see, we are really kind of comparing tan thetas, and they look like differential coefficients. So you would obviously kind of expect a relation with derivatives. So this lemma says that if your function is differentiable to begin with, then it's convex on an open interval. It's convex if and only if the derivative is increasing. So now, once I prove this lemma, I'll simply apply it to e to the power x, right? I mean, a convex function to begin with need not be differentiable. I have given you examples. So then you won't be able to formulate in terms of derivatives. That is why all this fuss about these coefficients, which is still at the top of the screen, the equation number 2. But if they are differentiable, then this inequalities involving quotients translates into plain and simple fact that the derivatives are that the derivative is increasing. So then e to the power x is of course convex after we know the lemma. Okay, so the way you prove the lemma is, I mean, it's not very difficult, but it's kind of a little exasperating. So take the points S, P, Q, T. Then what we have proved, phi P, P is the point after S, right? So phi P minus phi S by P minus S less than equal to phi Q minus phi P divided by Q minus P less than equal to phi T minus phi Q divided by T minus Q. That's exactly what the top line is. Note that. There the ordering of the points were S, T, U, S less than T less than U. So now just apply that. Okay. By the first and the third term, limit P going to S of phi P minus phi S by P minus S less than equal to limit Q going to T So if the function is convex and you have 2 points S and T, insert some 2 more points in between, get this inequality so that your S and T are very separate. That's what I wanted. And then you let Q go to T and P go to S, and you know the limit exists because the function is given to be differentiable and you are done. Conversely means what? Conversely, you are given a real differentiable function whose derivative is increasing. But if the derivative is increasing, then there is really nothing to prove because you want to prove that it's convex, right? Okay. Then 2 holds by mean value theorem. 2 is equivalent to convexity. That is 2 is equivalent to 1. 2 was this. Okay, I'll go where 2 is written. The number, yeah, that's 2 at the top of the screen, and that's equivalent to convexity. That's equivalent to equation 1, which was the defining criterion for convexity. And you want to show that 2 is satisfied. But how will you show 2 is satisfied? Well, phi is differentiable. So this phi T minus phi S by T minus S, this is some phi prime of, say, P between S and T. So phi prime of some point between S and T. And the right-hand side is phi prime of some point between T and U. S less than T less than U. So the first point is less than equal to the second point, and the derivative is increasing. So you are done. Okay. The straightforward application of mean value theorem. So consequently, so this completes the proof of the lemma. So consequently, we know that a real differentiable function is convex if and only if the derivative is increasing. Now you see, take any continuous, take any increasing function and integrate it. Maybe take an increasing continuous function so that it is possible to integrate it. You have to take an integrable function. So take a continuous increasing function and just integrate it. Whatever you get after integration, call that phi. Its derivative will be the original continuous increasing function that you took. And just the fact that that is increasing tells me that phi prime is increasing. So phi has to be convex. So integration of any increasing continuous function is convex. This gives you a lot of examples. Of course, x square, x power 4, etc., the even powers throughout real line. The odd powers in parts of the real line, etc., etc. I mean, umpteen number of examples, because Now you can integrate any continuous increasing function. Is that all right? Is that clear to everyone? Okay.
So
Yeah. Maybe you are muted. Okay. We hadn't proved this yet. That is, we started with a function and called it convex. I didn't take the function to be any nicer. This says that on an open interval, a convex function is continuous. Open interval is important, but because otherwise, suppose you take the closed interval 0, 1 and define the function to be identically 0 or everywhere except at the point 1. And at the point 1, the function is 1. Then note that your condition is satisfied. However, the function is discontinuous. So open interval is important. Take a compact subinterval. Choose C1 and D1 such that A less than C less than C1. No, A less than C1 less than C. I want to put C1 between A and C. And D less than D1 less than B. So CD is where? CD is right in the middle. So note that C less than X less than D. So C1 is below X, C1 is below C, below X is below D, below D1. All right. So then we have Fy minus Fx by Y minus X less than equal to Fd minus Fy by D minus Y because D is bigger than Y less than equal to Fd1 minus Fd by D1 minus D because D1 bigger than D. And at the same time, y minus fx by y minus x bigger than equal to fx minus fc by x minus c bigger than equal to fc minus fc1 by c minus c. I mean that inequality 2 being applied repeatedly, that's all. Okay. Showing that the set is bounded. Well, x and y are arbitrary. And the first inequality at the top of the screen shows that it's bounded above. The second inequality shows that it's bounded below. Okay. I mean, given x and y, you will choose first C, D. such that c less than x less than y less than d, and then you put c1 between a and c, and d1 between d and b, and so on. This can always be done. Okay. Is bounded by, say, m. So, but that, if that's bounded by m, what does this say? So mod fy minus fx less than equal to m times mod y minus x for all xy in AB. That's what this is saying. Maybe take x less than y. I mean, it doesn't matter either way. But then it has to be continuous, of course, as y goes to x. It's slightly better than continuous, in fact. Agreed?
Yes, sir.
Okay, good. So a convex function is always continuous. If it's differentiable, the derivative is increasing. If it's twice differentiable, the second derivative is positive.
So, sir, this condition is for Lebesgue continuous now.
Yes,
Okay.
that's what was shown. I didn't want to go into all that, but yes, you're right.
Sir,
Yes.
will it be for all x, y in CD or AB? This M
No,
depend on
no,
C and D, right?
Still, probably because the way I wrote it, you think that x choice of x and y depends on C and D. That's not the case. You could start with any x and y and choose a compact interval CD around it and contained in AB, right?
Yeah, and this bound M will depend on this CD, right? A convex function will be continuous, but it may not be Lipschitz continuous.
That is right. You have a point, Sushil. Thank you very much. Yes. It's Lipschitz continuous only on a compact subinterval.
Yeah, right. On every compact subinterval.
That's right. Thank you, Sushil.
Okay.
So it is continuous, and if the convex function is defined on an open interval, then on every compact subinterval it is Lipschitz continuous. Yes. The bound is depending on how we choose C and D. Right. You're right, Sushil. Yes. Okay. Jensen's inequality. I shall assume some familiarity with measures. Okay. Let this be a probability space if L1 mu function such that A less than F less than B, that is F is such a function that it lies between some two real numbers A and B. So this means A less than Fx less than B for all x in omega. And if phi is convex on AB, then integral is always over omega. I may not write it all the time. Then phi of the integral is less than equal to integral of phi composed with F. See, phi can be composed with F. And phi is convex on an open interval, so it's continuous, so it's measurable. So phi composed with f is measurable. So you can integrate it. I'll do the proof. The proof is very elegant. So let t be this number. Now f lies between a and b. So t lies between a and b because mu is a probability measure. When you integrate over the whole space, you get 1. That's why. I mean, I get a less than t less than b by simply using a less than fx less than b for every x and then integrating all 3 sides of the inequality. Okay, let beta equal to supremum a less than s less than t phi t minus phi s divided by t minus s. So phi t minus phi s divided by t minus s, as s varies between a and t, and phi is a convex function. Remember that. So this quotient really cannot be too big. Then in fact, beta less than equal to phi u minus phi t divided by u minus t for t less than u less than b. So rearranging this, I have phi u greater than equal to phi t plus beta u minus t. That's very simple. And from definition of beta, because beta is the supremum, beta is greater than equal to phi t. Here t less than u less than b. Beta is greater than equal to phi t minus phi s divided by t minus s, which on a rearrangement gives me phi s greater than equal to phi t phi s greater than equal to phi t plus s minus t beta. And this is for a less than s less than t. Now look at the two things. That is this and that. They together give me minus. For all s now, put together. Just look at the 2 lines where I have put the red marks. Now of course, since this holds for every s and fx lies between a and b, so phi of fx for every x greater than equal to phi t is for all x in omega. Now if we integrate, the last term is 0. That is how t has been chosen. I mean, if you integrate integral f minus t d mu, you will get integral f d mu minus t integral d mu. Integral d mu is 1. So t is the mean. So only the first term remains, and the integral has no effect on that because again integral d mu is 1. Okay. All right. I would like to conclude today with some examples. Now, note that, go back to the definition of a convex function. Is it possible to take 5 more minutes?
Yes, there is.
Okay. Go back to the definition of a convex function. Equation number 1. So do you notice what am I using there? All I am using is 1 minus lambda x can be added with lambda y. And similarly on the right hand side, I can perform an addition. So if I now take my phi, not defined on a subinterval of the real line, but actually on Rn, maybe on whole of Rn, maybe on a subset of Rn. then also I can do this 1 minus lambda x plus lambda y. X and y will now be elements of Rn. 1 minus lambda times x is an element of Rn. Lambda y is an element of Rn. I can add them. And if my phi is defined on whole of Rn, I don't even have to worry about whether I can apply phi on the addition or not, or cannot apply phi. So the first example is on Rn. This need not be the Euclidean norm. Take any good norm that you any norm that you like on Rn. The L1 norm, the sup norm, or whatever norm. Just by definition of norm, you will have norm of one minus lambda and lambda are positive numbers, so they come out of the norm as it is. There is nothing to prove, right? Let V be a subspace of Rn. We don't really need a subspace, but I don't want to enter into more concepts. So let phi x equal to infimum. Again, some norm, Rn with some norm. And well, this is called the distance of the point x from the subspace V. Okay. And this again is convex. It requires a little bit of a proof. The proof is very simple. Well, you want to show you want to show phi of 1 minus lambda x plus lambda y is 1 minus lambda phi x plus lambda phi y, but phi x is this infimum, or maybe I shouldn't use y here. The infimum is a limit of a sequence, right? So take a sequence, say un, such that norm x minus un goes to phi x. Take a sequence vn such that norm x minus vn goes to phi, norm y minus vn goes to phi y. So then we will be able to show that the sequence 1 minus lambda times un plus lambda times vn will actually satisfy that, will actually work for phi of 1 minus lambda x plus lambda y. So that's the homework. Do that, and that will give you this just from the triangle inequality of norm. The third thing is so note that I'm whatever I'm defining is on the whole of Rn. I'm not restricting to any subset. Be a symmetric linear transformation. But these are just for fun. It's not going to affect our LP spaces, but these are just for fun. And in case you want to pursue what is called convex analysis, which is a very rich subject in several variables and yields very high dividends. It's applicable in many areas. Okay. Let phi x equal to ax x. Then, so I've taken a symmetric A. If and only if A is positive semi-definite. I'll tell you one way of how to do it. You think about the other way. If A is positive semi-definite, you already know that A is symmetric, by the way. So that already tells you that the eigenvalues are real. And they can be ordered from the maximum to the minimum as lambda 1 greater than equal to lambda 2, etc. dot 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 greater than equal to lambda n. Lambda 1 is the maximum, lambda n is the minimum. A is only, okay, A is symmetric and positive definite. So lambda n greater than equal to 0. So lambda 1 greater than equal to lambda 2 greater than equal to dot 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 greater than equal to lambda n greater than equal to 0. Okay. Now, it's not very difficult to see that lambda 1 times norm x square greater than equal to ax inner product x greater than equal to lambda n times norm x square holds for every x. This is this part of what's called diagonalization. I mean, it's a consequence of diagonalization of symmetric matrices. Once you do that, after that, just try to figure out what is phi of, say, 1 minus alpha x times alpha y. I'm using alpha because I used lambda for the eigenvalues. It's a straightforward computation involving inner products, and you will be able to show that it's actually less than equal to what is wanted on the right side. And think about the converse. I gave these examples because you should know that this is a rich subject and it relates to metrics very, very well. Okay, I think I'll stop here. So we are meeting tomorrow.
Yes.
Okay. Any questions?
No, sir.